$4 billion. Just let that number sink in for a second. Back in 2017, Equifax, one of the biggest credit reporting companies in the US, had this absolutely catastrophic data breach. And the fallout? The legal settlements and damages, they hit an unbelievable, jaw-dropping $4 billion.
But it's not just about the money, right? The human cost is just wild. We're talking 147 million people who had their social security numbers, birth dates, their home addresses completely compromised. And here's the absolute craziest part of this whole disaster. The vulnerability that caused it, it wasn't some advanced, never-before-seen zero-day attack. It had been publicly known for months. It was literally sitting right there on a widely available security list. If just one person on that team had actually read this list, understood it, and taken action, this entire multi-billion-dollar nightmare could have been completely prevented.
So, welcome to The Explainer. I am super excited to dive into this with you today because we are demystifying the absolute most critical web security list you will ever need to know. Look, whether you're writing code, managing a product, or running penetration tests for a living, you really don't want to be the next Equifax. So, today we're unpacking the OWASP Top 10, specifically zooming in on the 2024 edition.
Here's our quick roadmap for today. We just covered the $4 billion mistake. Next, we'll officially meet OWASP. Then, we'll jump into the 2024 Top 10 list itself, talk about why these threats constantly evolve, and finally, wrap up with how you can actually secure your next project. All right. Part 2. Let's meet OWASP, basically the Wikipedia of web security.
So, OWASP. It stands for the Open Worldwide Application Security Project. And it's really important to know what it isn't. It's not a government agency, and it's definitely not some corporation trying to sell you an expensive product. It's actually a completely free, community-driven, nonprofit foundation. It's run by thousands of security pros and developers all over the world. Now, web application security is notoriously difficult, and let's be honest, most developers just don't get trained on it in school. So OWASP asked a really brilliant question. If we could teach developers just one crucial thing about security, what would it be? And their answer is the Top 10 list. It's essentially a roadmap of the 10 absolute most dangerous vulnerabilities that, well, you're probably introducing into your codebase right now without even realizing it.
Let's get right into it. The 2024 Top 10 list, the most dangerous vulnerabilities out there.
Coming in hot at number 1, we have broken access control. Now, to really grasp this, we've got to clear up a massive misconception. It all comes down to the difference between authentication and authorization. Authentication is just proving who you are, like logging in. But authorization is what you're actually allowed to see or do once you're through the door. A lot of lazy development assumes that, hey, if a user is logged in, they can basically do whatever. Imagine logging into your bank, right? You look up at the URL bar and it says user/1234/account. What if you just change that 1234 to 5678? If the app suddenly shows you someone else's bank balance, boom, the application totally failed to check if you actually had the authorization to view account 5678. That is broken access control in a nutshell. And guys, it is everywhere. Moving on to number 2, cryptographic failures. This happens when an app basically drops the ball on protecting sensitive data. Think about a website that stores passwords in plain text instead of hashing them. Or maybe the data is encrypted, but oops, the encryption key is just hard-coded right there in the source code for anyone to easily find. The absolutely crucial takeaway here is this. Once unencrypted or weakly encrypted data gets stolen, that's it. It's gone forever. There is no undo button. You've permanently lost the trust of your users. Number 3 brings us to an absolute classic in the security world, injection. This usually crops up when untrusted data is fed directly into a system's commands. Take the famous SQL injection string as an example. Picture a standard login box. Instead of typing a normal username, a hacker types admin, or, 1, equals, 1. Now, if the code isn't properly protected, the database reads that as a literal query asking, hey, is the username admin, or does 1 equal 1? Well, 1 obviously always equals 1, so the whole thing evaluates as true, the system completely bypasses the password check, and just like that, the attacker is logged in as the administrator. It's terrifying, honestly, because it can lead to a total system compromise in seconds. Okay, let's group vulnerabilities 4, 5, and 6 together, because they all kind of represent these massive architectural and operational blind spots. Number 4 is insecure design. Now, this isn't really about writing bad code. It's about an architecture that's flawed right from the drawing board. Like imagine an app missing basic rate limits, meaning an attacker can run a script to guess 1 million passwords a second with zero throttling. Next is number 5, security misconfiguration.
Think about those default admin/admin passwords that get left enabled in production environments, or maybe leaving debug mode turned on. This happens all the time when teams prioritize shipping fast over shipping securely. And rounding out this group is number 6, vulnerable and outdated components. Your own code might be perfectly secure, but if it relies on some super old open source logging library that has a known remote code execution flaw, yeah, you're leaving the front door wide open for attackers.
All right, rounding out the back half of the list, we have a rapid-fire mix of really critical threats. Number 7 is authentication and session management failures. We're talking predictable session IDs or passwords that literally never time out. Number 8 is software and data integrity failures. This is when malicious code manages to sneak its way into your automated deployment pipelines, your CI/CD, or maybe through compromised third-party dependencies. Number 9, logging and monitoring failures. Simply put, if you don't keep logs of what's happening on your servers, you won't even know you've been hacked. Plus, you can't prove to regulators exactly what got stolen. And finally, number 10 is server-side request forgery, or SSRF for short. This is where an attacker essentially tricks your server into reaching out to internal networks, potentially exposing highly sensitive internal cloud metadata. So when we step back and look at that whole list, a pretty huge theme starts to emerge. These aren't just simple little coding typos. Real security requires thinking across your entire stack. We're talking about the architectural design, the operational deployment, the people you hire, and the processes you follow day in and day out. It is a completely holistic challenge, not just an IT problem. Moving on to our next section, why the threats evolve, a living threat landscape. Now, you might be wondering why this list changes over time. Well, it's strictly data-driven. It's based on what attackers are actually exploiting in the real world right now. If we look back at 2017, certain vulnerabilities were absolutely massive, but by 2024, they actually dropped off the list entirely because companies finally adopted better frameworks to fix them automatically. But the landscape always shifts. Look at 2021. The huge surge in cloud adoption and microservices introduced completely new architectural risks. For example, that SSRF vulnerability we just talked about, that wasn't even on the 2017 list, but modern cloud metadata services turned it into a critical attack vector today. Add to that the fact that security researchers are constantly discovering new ways to break things. So what you learned back in 2017 is, frankly, dangerously incomplete in 2024. And that brings us to the final part of our explainer, securing your next project, your actionable playbook. We always hear that security is everyone's job, right? But your specific homework really depends on your daily role. If you're a developer, your job is to review your code against these specific vulnerabilities and start leaning heavily on security-focused tools. Actually, I highly recommend checking out OWASP's WebGoat training. It's completely free, and it's specifically designed to give you hands-on experience with exactly these concepts. Now, if you're a security engineer, you absolutely need to make the top 10 mandatory on your penetration testing checklists, so you're systematically testing for every single one of them. And if you're a manager or a tech leader, you've got to make sure your team actually knows this list inside and out. Bake it into your onboarding, use it to prioritize your technical debt, and definitely reference it when you're discussing risk with upper management. Look, simply memorizing the OWASP top 10 isn't going to magically turn you into some master hacker overnight, but it absolutely will keep you from making those obvious, catastrophic mistakes that literally cost companies billions of dollars. Today, we're pulling back the curtain on the web's structural vulnerabilities. We're going to break down the big three, the absolute most pervasive web vulnerabilities out there: SQL injection, cross-site scripting, and cross-site request forgery. And we're doing it using a structured, visual approach. So if you've ever wondered exactly how hackers bypass modern web applications, well, this is exactly where it all starts. Now look at this number, $18.5 million. That was the settlement cost alone following the massive 2013 Target data breach. Attackers managed to steal 40 million credit card numbers, compromising a staggering 70 million personal records in total. But how did the real damage actually happen? It wasn't some wildly complex Hollywood-style sci-fi hack. No, the attackers simply exploited the fundamental trust of a web application to inject malicious code directly into the system, harvest those millions of credit cards, and completely vanish. Okay, let's dive right into our roadmap for today. First, we'll look at the cost of blind trust. Then we'll dissect SQL injection, cross-site scripting, and cross-site request forgery. And finally, we'll wrap the whole thing up with the golden rule of defense. Let's get to it. Section 1, the cost of blind trust, and exactly how attackers exploit assumptions. To really grasp these vulnerabilities, we first have to understand why they even exist in the first place. You see, applications dangerously assume that logged-in users and web forms are naturally safe. Because of that blind trust, attacks tend to follow a pretty universal pattern. 1. User input isn't validated. 2. That unverified data enters the system. 3. The code blindly trusts it. And 4. The attack executes. It's absolutely crucial to understand that attackers don't actually break the application. They just work around it by weaponizing that unverified trust. Before we look at a single line of code, let's map these highly technical concepts to a physical scenario. Think of application security like a nightclub bouncer. SQL injection? That's like handing the bouncer a fake ID that basically says ID or 1 equals 1, which translates to always true. The bouncer glances at it, doesn't check the underlying logic, and just lets you right in. Cross-site scripting, or XSS, is like handing that bouncer a note that says, hey, let my friend in too. The bouncer actually reads it aloud to the crowd, and everyone blindly follows the instruction. And then there's cross-site request forgery, or CSRF. That's like forging a note from the club owner saying, give this person free drinks. The bartender doesn't bother to verify who actually wrote it, and boom, you get the drinks. Moving on to Section 2, SQL injection, or SQI, bypassing the logic. Now, what's really interesting here is how simple the flaw actually is. As a massive mainstay on the OWASP top 10, SQI is literally one of the oldest and most devastating ways to hack an app. It works because the application concatenates, or essentially glues together, user input directly into SQL queries without actually checking it. It's kind of like a game of Mad Libs where the user gets to provide some of the words. The developer asks a simple question, but the user completely hijacks the underlying sentence structure to do whatever they want.
So what does this actually look like in practice? Let's say you have a standard login page. Instead of entering a normal password, an attacker types this specific malicious payload into the password field. Quote or quote 1 equals quote 1 quote. Now, because the number 1 always equals the number 1, this condition is mathematically always true. When the application runs the database query, it just returns the admin user regardless of what the actual password is. Just like that, the attacker bypassed authentication entirely. Crazy, right?
But the damage goes far beyond a simple login bypass. Once that door is open, SQL injection becomes incredibly powerful. An attacker can modify their input to do something much more destructive. A command like drop table users, if executed, literally deletes the entire user database. The whole thing, just gone in a millisecond. Alternatively, they can inject commands to extract every single credit card stored in the payments table, which is exactly how those massive, headline-making breaches actually happen.
So how on earth do we fix this? Well, the defensive strategy is actually remarkably straightforward. You need to use parameterized queries, which are also known as prepared statements. Instead of building a string, you use placeholders. This forces the application to treat the malicious payload strictly as data, not as executable code. No matter what the user enters, the application treats it as just a string of text, meaning it literally cannot break the SQL structure. Bottom line, never concatenate user input, and whenever possible, use an ORM tool that handles all of this for you automatically. All right, Section 3, Cross-Site Scripting, or XSS, attacking the browser.
What makes XSS so unique is its target. Instead of attacking the web server directly, this vulnerability actually weaponizes the victim's own web browser. It happens when an attacker injects malicious JavaScript code into a web page. Then when a victim visits, their browser just executes the code. Why? Because the browser literally cannot tell the difference between legitimate application code and injected malicious code. If it's on the page, the browser runs it, no questions asked. Now, this is a classic example of reflected XSS. An attacker creates a manipulated URL containing a script and tricks a victim into clicking it, usually through a phishing email. When they click, the application takes that input from the URL and reflects it straight back onto the page. The script runs, and typically for a proof of concept, you'll see a little pop-up that says hacked. But let's be real, an actual attacker wouldn't show you a pop-up. They would use the script to silently steal your session cookie, which allows them to log right into your account without even needing your password. And that brings us to a much more dangerous variant, stored XSS. See, reflected XSS requires tricking the victim into actually clicking a link. Stored XSS, it doesn't. Imagine an attacker leaves a comment on a social media site containing this payload. That malicious comment is permanently stored in the site's database. Now, every single time anyone views that comment section, their browser executes the script and their session cookie is automatically sent straight to the attacker. The entire attack happens completely automatically.
To properly defend against XSS, developers absolutely must filter out JavaScript before displaying user input. We do this through output encoding, which basically means escaping HTML characters. You're turning executable code brackets into safe literal text representations. When you encode the output, the browser just sees it as literal text and won't execute it. Plus, implementing a robust content security policy tells the browser to only run JavaScript from strictly approved sources, which completely neutralizes those injected scripts.
Next up, Section 4, Cross-Site Request Forgery, or CSRF, the hidden action.
While XSS attacks the browser to steal data, CSRF is arguably the sneakiest of the three because it abuses normal browser functionality to force the user to perform legitimate actions completely against their will. Let's step through the mechanics here. Say you log into your bank securely. Without logging out, you open another tab and happen to visit a malicious website. That malicious site contains hidden code that automatically makes a request to your bank. Because you're already logged in on that other tab, your browser faithfully attaches your valid session cookie to the request, completely processing a transfer you never actually wanted to make.
Here's exactly how simple the exploit can be. An attacker hides an HTML image tag on their site. To the browser, it looks like it's just trying to load a tiny image, but the source URL is actually a state-changing request to transfer $10,000. Your browser tries to load the image, inherently sends your active bank session cookie right along with it, and the bank processes it because, well, it legitimately looks like it came from you. The attacker totally exploited the fact that browsers automatically send cookies with requests to the same website. So the defense against CSRF requires verifying actual intent. And the most effective way to do that is by using CSRF tokens. When a user visits a form, the server generates a unique random token. It's essentially an unforgeable secret handshake. When the form is submitted, the server checks if that token is valid. Since the attacker in the other tab can't see or guess this token, the forged request is immediately rejected. Also, modern browsers support the same site cookie attribute, which simply tells the browser to never send your cookie if the request originated from a totally different website.
Finally, Section 5, the golden rule of defense. Trust nothing. We've covered 3 very different attacks today, but they all stem from the exact same thing: unverified assumptions. So if you take away anything from this explainer, let it be this single, unified golden rule. Never trust user input. Always validate on the server. Always encode output.
Welcome, everyone, to The Explainer. I am absolutely thrilled you're tuning in today, because we are tackling the ultimate guide to understanding the literal #1 reason web apps get hacked. You know, you might think you're totally secure when you log into your favorite sites, but under the hood, man, developers are making some critical mistakes in how they verify exactly who you are and, more importantly, what you're actually allowed to do. So today, we're decoding these vulnerabilities straight from the source material and turning those complex cybersecurity concepts into some clear, actionable blueprints. To truly grasp the stakes here, we've got to rewind to 2012. 6.5 million. Just let that number sink in for a second. That is the exact number of user passwords stolen in an absolute flash during a catastrophic breach at LinkedIn. Hackers didn't just break into a system. They literally walked away with the master keys to millions of digital lives. But, how does something on that massive of a scale actually happen at a major tech giant?
Well, the problem wasn't just the breach itself, it was the massive domino effect it caused across the entire internet. See, LinkedIn used a weak, super outdated hashing algorithm called MD5 to protect those passwords. And because MD5 can be cracked in less than a second using modern tools, hackers just flipped those stolen hashes right back into plaintext passwords within days. And here is where the true disaster hits. Because let's be real, we humans are creatures of habit. People reuse their LinkedIn passwords for their Gmail, their Facebook, their Twitter, even their bank accounts. An off failure at one single company cascaded like wildfire across dozens of others. It was a massive wake-up call for the whole industry.
Okay, let's dive into this. Here is our roadmap for The Explainer today. 1. Auth versus auth. 2. Attacking identity. 3. Bypassing permissions. And 4. The secure blueprint.
Section 1. Auth versus auth, the fundamental distinction.
Let's make this crystal clear with a real-world analogy. Imagine you're walking into an airport. Authentication is proving who you are at the check-in desk, right? You hand over your driver's license, and the agent checks, is this actually John Smith? Does the photo match? Once verified, the system knows your identity. You're authenticated. But authorization is what you're actually allowed to do based on who you are. The TSA agent checks your boarding pass. Are you flying first class or economy? If you're authorized, you board. If not, you're stopped at the gate. The massive failure happening in web dev right now is that engineers get the check-in part right. You log in. but they totally forget to check your boarding pass. They just assume if you're in the building, you can do anything.
And that exact assumption led to one of the most infamous vulnerabilities in tech history. Facebook actually had a bug where you could view any user's private friend list simply by changing the URL to point to a different user ID, like just changing the number at the end to 12345. Facebook's code perfectly verified the authentication. It asked, "Hey, is this user logged in?" And the answer was yes. But it completely failed to check the authorization. It never bothered to ask, wait, does this specific user have permission to view this specific profile? Because of that one single missing check, billions of people's social networks were exposed. Authentication was checked, but authorization was just skipped entirely.
Section 2. Attacking Identity. Critical Authentication Failures.
So let's talk about how companies actually store your passwords. If an attacker gets their hands on a database, the hashing algorithm used makes all the difference in the world. And this brilliantly illustrates why modern hashing is absolutely non-negotiable. If a company uses MD5 like LinkedIn did, an attacker using a tool like Hashcat can crack it in less than a second. Shot 1 isn't really much better, taking maybe 1 to 10 seconds. But look at bcrypt. It's intentionally designed to be slow. It takes about a full second just to hash one password on the server. So, if an attacker tries to crack millions of them, it would literally take them years, or honestly even lifetimes. Using bcrypt or Argon 2 is the absolute gold standard for keeping identities safe.
Now let's see how this builds into an entirely different kind of attack: session hijacking. When you log in, the app gives you a session token. Think of it kind of like a stamp on your hand at a club. You show it with every request so you don't have to keep typing your password. But what if those tokens are completely predictable? Like if your session token is 1001 and the next user gets 1002, an attacker can just log in, get token 1003, and then easily guess the token 1004 belongs to someone else. They swap their token out, and boom, they've hijacked an active user's account without ever needing their password. Tokens absolutely have to be cryptographically random to be secure.
All right, before we move on, we've got to speed through a few simpler yet completely deadly authentication failures that developers somehow still make. First, no rate limiting. If you don't limit login attempts, a hacker can just run a script trying a million passwords a second until they get in. Second, shipping apps with default credentials like admin and password. Attackers literally just look those up in the documentation. Third, lacking multi-factor authentication, or MFA. Relying on just a password means if it's stolen, the account is totally gone. And finally, predictable password reset links. If your forgot password link relies on a super simple, guessable token, an attacker can easily reset your password for you and lock you completely out.
Section 3. Bypassing permissions. Critical authorization failures.
Now, what's really interesting about this is what happens after a hacker gets inside. Enter the IDOR attack, Insecure Direct Object Reference. It sounds super technical, but it's incredibly simple and absolutely devastating. Say you log into your bank. You look at the URL and it says account ID equals 54321. As an attacker, you just click the URL bar, delete the 1, type a 2, and hit enter. If the application doesn't verify that you actually own account 54322, boom. You're now looking at someone else's full account balance and transaction history. Literally just changing a number in a URL exposed highly private data, all because the server didn't verify ownership.
Building right on that, we have vertical privilege escalation. Imagine you're a regular employee just updating your profile. When you hit save, your browser sends a hidden request to the server. Well, an attacker can use a proxy tool to pause that network request midair. They look at the data being sent and notice a little field that says role equals user. They simply delete the word user, type in admin, and forward the request to the server. If the server trusts that user input, instead of checking a secure backend database, that regular user is instantly elevated to an administrator. Total system compromise. You can never, ever trust user input for role.
There are a few other nasty authorization traps to watch out for too, like leaving endpoints such as /admin/delete user totally unprotected, just assuming nobody will ever guess the URL, or using API tokens like JSON web tokens that never expire, meaning if a hacker steals one, they have access literally forever. But the biggest trap of all? Hiding UI buttons instead of protecting the actual API. Developers will hide a delete button on the screen for regular users and think they've secured the app, but the backend server endpoint itself is still totally active. Look, a hacker doesn't need your button. They just send a raw request straight to the server. If the server isn't strictly enforcing authorization, that hidden button is utterly useless.
Section 4. The Secure Blueprint. Fixing the Failures. Okay, So how do we actually fix this? This is the exact secure life cycle of how a session token must be handled so an attacker can never steal or hijack it. Once a login is properly validated, the server absolutely must generate a cryptographically random token with high entropy. Then it has to be stored in a secure HTTP-only cookie on the user's browser. That HTTP-only part, it's magic. It means malicious JavaScript can't read the cookie, which neutralizes entire categories of attacks. Finally, that session needs an absolute expiration time, say 15 minutes of inactivity. So even if a token is somehow intercepted, its window of usefulness slams shut super fast.
So the crucial point is really this checklist right here. Number 1, you must use HTTPS always to encrypt data in transit. 2, you must hash your passwords with bcrypt or Argon2 to protect them at rest. 3, you must validate the user session token on literally every single request. And finally, number 4, you must check permissions server side. Never, ever trust the client or the URL parameters to dictate what a user is allowed to do.
I really want to drill this home with a core mantra from our sources to summarize everything. Memorize it, write it on a sticky note, stick it to your monitor. Authentication proves who you are. Authorization proves what you can do. Both are required. If you implement one without the other, your application is just a sitting duck. It's an unshakable rule of web security.
Hey everyone, welcome to this explainer. Today, we're diving into something that's practically invisible, yet absolutely critical, the threat surface of our modern applications. You know, we spend so much time making sure our websites look amazing and function securely, but running quietly in the background is the digital plumbing that powers the entire internet. And honestly, if that plumbing isn't secure, the whole shebang falls apart.
To really grasp the stakes here, let's look at a staggering number: $100 million. Yeah, you heard that right. That is the estimated cost in damages and fines from the massive 2022 Uber breach. And how exactly did hackers get their hands on the personal information of thousands of customers? We're talking names, phone numbers, ride histories. It wasn't some wildly sophisticated zero-day exploit. Nope. It was a single leaked API key. With just one key, attackers literally unlocked the kingdom.
So how does something like this happen right under our noses? Well, Uber's website was completely secure. Their mobile app, totally secure. But their API was exposed. And this brilliantly illustrates the blind spot we're talking about today. Websites return HTML, right? They're visual, built for humans to read and interact with. APIs, on the other hand, return raw data, like JSON or XML. They are built for machines to read and process automatically. Because we humans don't actually see this raw data floating back and forth, vulnerabilities can easily slip by unnoticed.
All right, now that we've established the devastating stakes, here's our roadmap for building an impenetrable defense today. We'll cover the invisible attack surface, compare API authentication methods, dig into critical API vulnerabilities, look at strategies for rate limiting, and finish up with best practices for secure APIs.
Let's jump right into part 1, the invisible attack surface.
Think about a traditional website. It basically has one main attack surface. But an API? Wow. It's a completely different beast. Every single endpoint, every method, whether it's a GET, POST, or DELETE request, and every single parameter is a potential entry point. A company might have 50 tightly protected website endpoints, but 500 API endpoints. Because they're invisible to users, security teams just forget them. They're always accessible programmatically, which means attackers can automate exploits in seconds. Plus, one API serves multiple clients: web browsers, mobile apps, third-party integrations. Because of this massive, diverse ecosystem, we can't just rely on traditional browser session cookies for security anymore.
Which brings us to part 2, comparing API authentication methods.
Since those old-school session cookies are basically useless when a mobile app or a script is making a request, we have to look at the specific tokens used to shield our invisible endpoints. Enter the JSON Web Token, or JWT. Its structure is actually pretty fascinating. A JWT contains information about the user and is broken into 3 parts. You have the header, which tells us the algorithm used, the payload, holding the actual user data, and the signature, proving the token hasn't been tampered with. But listen carefully to this next point. The payload is only encoded, it is not encrypted.
And here's why that distinction is literally a make or break deal. Look at these payloads. A safe payload contains totally harmless data, stuff like a user ID, a username, an email, or an expiration timestamp. That's totally fine. But a dangerous payload? That might include a password or a credit card number. Because a JWT is simply base 64 encoded, anyone, and I mean anyone, who intercepts this token can just paste it into a free web decoder and read your sensitive data in plain text. You absolutely must never put passwords or sensitive financial data in a JWT payload.
Okay, let's pivot over to our next authentication framework, OAuth 2.0. If you've ever clicked a Login with Google or Login with Facebook button, you've used OAuth 2. It's basically a framework for delegated access. Here's how it flows. The user wants to log in, so the app redirects them to Google. The user verifies their identity directly with Google, and Google asks, hey, should this app access your profile? Once you say yes, Google issues a token back to the app. The absolute game changer here is that your app never actually sees the user's password. Only the provider holds it.
So stacking these up side by side, a pretty clear picture emerges. API keys, like the one that cost Uber $100 million, are incredibly simple to set up, but their security is super low. They rarely expire, and you have to manually revoke them. JWTs offer a nice middle ground. They do expire, but trying to revoke them before they expire is notoriously difficult. Then there's OAuth 2.0. It's definitely complex to implement, no doubt about it, but it provides the highest security, makes token revocation super easy, and is absolutely the best option when you are handling sensitive data.
All right, part 3, critical API security vulnerabilities. Let's look at exactly how attackers are picking these digital locks. First up on the hit list is Broken Object Level Authorization, or BOLA. Picture this. An attacker logs in and their API request asks for user profile 12345. But what happens if they just tweak that URL to ask for profile 54321 instead? In a vulnerable API, the server just blindly hands over the other person's profile because it never actually checked if the requester owns the data. The fix for this is elegant and it's essential. Your code must explicitly check if the requested user ID matches the currently logged in user. If it doesn't, boom, return a 403 forbidden error immediately.
Next up, we have excessive data exposure. Let's say an app makes a request to get a user's basic profile just to display their name and email on screen. But the API responds with their name, email, phone number, social security number, their salary, and even their password hash. A developer might naively think, well, the mobile app will just politely hide the social security number. That is a massive failure. Remember, the attacker isn't using your polite mobile app, they are querying the API directly. Never ever return unnecessary fields.
And then there's mass assignment, which is honestly just as terrifying. This happens when a clever user modifies fields they really shouldn't have access to. Say you have an endpoint for a user to simply update their email address. What if they intercept the post request and inject an extra line of code that says role equals admin or salary 500,000? If the API just blindly accepts all incoming fields and updates the database, that user literally just promoted themselves to a highly paid system administrator. The only proper fix here is strictly whitelisting the specific fields, like name, email, and phone, that a user is actually allowed to modify.
Moving right along to part 4, strategies for rate limiting.
Why do we care so much about rate limiting? Well, look at this. It is terrifyingly simple for an attacker to whip up a 2-line Python script that hits your server 1,000,000 times in a matter of seconds. Without protection in place, your server is going to do one of two things. It'll either crash entirely, or the attacker will successfully scrape every single piece of data you hold. To stop that from happening, we've got a few different rate limiting strategies in our toolkit. You can use a user-based strategy, which limits requests per logged-in account, or an IP-based strategy, limiting requests coming from a specific IP address. You can even get more advanced with a sliding window, which tracks requests smoothly over a set time frame, or a token bucket, which allows for brief, legitimate bursts of traffic while capping the overall rate. When a script hits these limits, your API instantly defends itself by throwing up a 429 too many request status code. Which leads us perfectly into our final section, best practices for secure APIs. We've seen the massive breaches, the vulnerabilities, the scary attack scripts, but here is the really good news. Building an unbreakable API is totally within your control if you follow the right architecture from day one. There are a few core non-negotiable takeaways here. First, always use HTTPS. Never transmit data over unencrypted HTTP. Second, check authorization on every single endpoint. Don't just assume a user is safe because they logged in. Verify they actually own the specific resource they're asking for. And finally, adopt a strict policy of deny by default. Only allow access when you have explicitly programmed an exception. Layer your defenses, log your API access to monitor for weird traffic patterns, and frankly, never trust the client.
Welcome to The Explainer. Today we're cracking open a toolkit that is absolutely going to change how you build software. We're going to unpack the 7 core principles of secure coding. Because let's be real, we need to move past just making things work and actually build a truly secure mindset together. Let's get right into it.
Okay, I want to start with a number that should honestly make any developer sweat a little bit. $10 million. Back in 2018, a developer at a major e-commerce company wrote just one single line of vulnerable code. It was a SQL query, and they forgot to sanitize the user input. Well, within weeks, hackers found it, exploited it, and exposed 150 million customer records. We're talking names, addresses, credit cards, the whole shebang. The company ended up paying $10 million in settlements. Now, that developer, they definitely didn't wake up that morning wanting to cause a massive data breach. They probably had no idea their code was even vulnerable. And, that really hits the nail on the head regarding the invisible threat we're all facing. Most developers learn to write code that works, not code that's secure. And those are two massively different things. Think about it. Standard computer science programs almost never teach secure coding as a core fundamental. Plus, out in the real world, startups are always pushing for speed and shipping features over taking the time to lock things down. It creates this totally false sense of security where we just assume, hey, we've got a firewall, the application itself doesn't need armor. But it absolutely does. Which brings us to Section 1, the $10 million mistake, and why vulnerabilities actually happen. What is super interesting here is where the actual threat is coming from. According to OWASP, an absolutely staggering 80% of web app vulnerabilities come directly from insecure code. Not misconfigured servers, not unpatched systems, just bad code. If you look at the breakdown, input validation errors alone make up a massive 30% of these mistakes, and that's followed closely by weak authentication at 25% and authorization failures at 20%. So this tells us exactly where we need to focus our efforts first if we want to stop these breaches. Let's move to Section 2, gatekeeping, specifically looking at inputs and outputs. All right, Principle 1, input validation. Basically, this just means checking that the data hitting your application is exactly 100% what you expect it to be. Take a look at the bad approach first. Here, the developer just grabs an email and phone number and saves them, period. No validation whatsoever. A malicious user could easily slip a destructive script right in there instead of an email. Now, compare that to the secure approach below it. This developer is using strict server-side whitelisting with regular expressions. They are literally saying, look, I'm only going to allow these specific characters, A through Z, 0 through 9, and the @ symbol. That's it. And notice I said server-side. Always whitelist on the server, guys. Never just trust the client side. Now, if input validation is checking what comes in, Principle 2, output encoding, is all about managing what goes out. Output encoding is your main defense against cross-site scripting or XSS attacks because it forces the browser to treat user content as literal data, not executable code. Just imagine a user submits a blog comment, but hidden inside that text is a script designed to steal other users' browser cookies. If your app just carelessly displays that comment as is, the victim's browser is going to execute that malicious script, no questions asked. To see this in action, check out the vulnerable approach on top. The user's comment gets injected straight into an HTML tag. Yikes. But right below it, in the secure version, the developer is importing a specific escape function. By applying that HTML escape encoding, those dangerous sneaky script tags are transformed into harmless literal text entities. The browser just displays it as plain text. It completely ignores it as a command. And remember, context is everything here. HTML, JavaScript, URLs, they all require slightly different types of encoding, so make sure you're using the right tool for the job. So let's fast forward a bit and do a quick rapid fire on Principle 7, because it perfectly ties all this gatekeeping together. Simply put, never trust user input. Whenever you see user input, I want you to immediately assume it's malicious. Not because your users are out to get you, but because attackers can easily manipulate it. Just look at the sheer scale of the attack surface we're dealing with. We aren't just talking about form submissions. We're talking URL parameters, cookies that can be forged, spoofed headers, API requests, file uploads, even session data. You have got to validate and encode absolutely everything, every single time. All right, let's jump into Section 3, locking down your data. Okay, Principle 3, parameterized queries. This right here is exactly how we prevent that $10 million injection mistake we talked about at the very beginning. Look at the vulnerable string concatenation on top. The query is literally just gluing the user's raw input directly into the SQL command. So if someone types in admin or 1 = 1, they've just completely rewritten your query logic and bypassed the login. Boom.
But look at the secure version. By using parameterized queries, you see those little placeholders in the SQL string? You are completely separating the SQL structure from the data itself. The database interpreter is forced to treat the user input purely as a literal string. It makes SQL injection mathematically impossible. It's a total game changer. Moving a bit deeper into the backend, we hit principle 4, least privilege. The golden rule here is incredibly simple. Give your code and your users only the absolute minimum permissions they need to get their job done. Do not, I repeat, do not give admin access to everyone just because it's easier to debug. If user A only needs to read and write their own profile data, don't give them read access to the entire user table. And please, for the love of all things secure, never run your web applications as root. Just don't do it. Let's look at a super practical example. Imagine a payment processing function. The top snippet is bad news, because that function just has broad access to the entire database. A tiny little logic error there could accidentally trigger a delete_user command, or worse, wire money to an admin account. But the bottom version? That demonstrates least privilege perfectly. The function only pulls exactly what it needs, the user's current balance, updates it, and saves it back. It literally lacks the system permissions to delete an account or access admin tables. By artificially limiting that privilege, you dramatically shrink the blast radius if that function ever gets compromised.
Next up is Section 4, fail-safes and layered defense. This brings us right to Principle 5, defense in depth. The core concept here is that you should never, ever rely on just one single security measure. Think of your application like a giant medieval castle. Your network security? That's the moat. Firewalls are the heavy outer walls. Your access controls act as the inner walls. Monitoring systems are the guards walking the perimeter. And encryption at rest is the heavy iron vault in the center. If an attacker manages to cross the moat, the outer walls are there to stop them. If they scale the walls, the guards catch them. The idea is that if one layer completely fails, the underlying layers are still there to catch the bad guys.
Grounding this back in our day-to-day coding reality, look at how we can apply these multiple layers to just a single Python function. The bad example on top relies entirely on the function's internal logic, but the secure example, that's defense in depth in action. We've got a decorator handling authentication as layer 1, another decorator handling authentication as layer 2. Inside the function, we've got code-level ownership checks as layer 3, the database itself filters the query as layer 5, and finally, we log the access attempt for our monitoring system as layer 6. Now that is a highly resilient, beautifully layered piece of architecture. Okay, but what happens when things inevitably crash? That brings us to Principle 6, secure error handling. When errors occur, you must never reveal sensitive information back to the user. Say your database connection drops, and your app just dumps the raw stack trace right onto the user's screen. Well, you might have just handed an attacker your server paths, your internal IP addresses, and maybe even your database credentials. I'm telling you, stack traces leaking in production are an absolute goldmine for hackers. So how do we handle this gracefully? Check out the bottom block of code here. Instead of spitting that massive, scary exception string back to the user, the developer catches the exception gracefully. They use a logger to record that highly detailed, sensitive stack trace internally so the engineering team can actually fix it, but then they return a safe, super generic message to the user like, login failed, please try again. You still get to track and fix the bug, but the attacker learns absolutely zero about your backend infrastructure. Win-win.
Finally, Section 5, practicing secure coding. We've talked theory. Here is your concrete developer's toolkit to actually make this a habit. First, embrace pure code reviews. Seriously, another pair of eyes will catch the dumb mistakes we all make when we're tired. Second, integrate static analysis tools, things like SonarQube or SumGrip, right into your CI/CD pipeline. They'll automatically scan your code for vulnerabilities before you even merge. Third, get some hands-on practice. Go play around on intentionally vulnerable apps like OWASP WebGoat so you can actually see how these exploits work in the wild. Bookmark the OWASP cheat sheets for whatever language you write in. And lastly, start writing unit tests specifically for security. Write a test that literally shoots a SQL injection payload at your function just to prove it fails safely. Ultimately, the biggest takeaway here is a total mindset shift. The old way of building software was to blindly write features, deploy them, and then maybe bolt some security on at the end if the budget allowed. But it's way too late by then. The modern workflow is all about the secure software development lifecycle, or secure SDLC. You plan for security during requirements gathering, you code securely from the very first commit, and security testing happens right alongside your feature testing, not as an afterthought.
I really want to leave you with this thought. The software industry is changing rapidly. Security is no longer an optional nice-to-have. It's an absolute baseline expectation from day one. Companies aren't just asking if you can code, they're specifically asking if you can write secure code. So master these 7 principles. Validate your inputs, encode your outputs, parameterize those queries, enforce least privilege, build defense in depth, handle your errors securely, and literally never trust user input. If you can do all that, you become incredibly valuable to any team. But if you can't, honestly, you're a liability.
So to wrap up this explainer, I have a challenge for you. I want you to reflect on your own code base right now. What's the most common security mistake you keep seeing in your team's code reviews? And be honest with yourself. Which of these 7 principles do you personally struggle with the most? Keep those questions in mind, go take a hard look at your code today, and start building that unhackable perimeter. Keep learning, keep questioning, and I will see you in the next explainer.